So we're going to look at some algebraic properties of limits, or essentially some limit laws. We're going to see how we can use these laws to help us deal with more complicated expressions. So we're going to start with the constant term here. So the constant term doesn't affect limits. Okay, so basically what we can do is we can take the limit of the function and apply the constant afterwards. With sums and differences, we can again separate these out. We can take the limit of one function and add it to the limit of the other function. Similarly, with multiplication of two functions, we can take the limit of one part, limit of the other part, and multiply them together instead of taking the limit of the more complex expression. And if we can do this for multiplication, we can certainly do this for division. So we can, if we have the limit of a quotient, we can take the limit of the numerator and compare it to the limit of the denominator. So this also works with powers. Okay, so if I have a function to some power, what I could do is I can actually work out the limit of that function first and then apply the power after the fact. And well, it's not conversely, but similarly, if the exponent is the function and we have a limit of an exponent with some constant base and a function for the exponent, we can take the limit of the function in the exponent first and then apply it to the base. Okay, so we take a look at some examples here. So in this case here, we have the limit of sine going to 0. So we have this base here, which is a function. We have it multiplied to another function here. What we can actually do is we can do this. We can take the limit, and I'm going to do this in different colors. So we can take a look at that sine function, and we can actually take the limit as x goes to 0 of the sine function first, and then afterwards we can apply the exponent, and we can also do the limit of the cosine of that separately, okay, and multiply the limit of the cosine separately. Similarly, with the plus part here, we can do the same thing. So we can take the limit of the numerator, so limit as e to the x as x goes to 0. Okay, and forgot the x goes to 0 here. X goes to 0, and we can apply that limit to just the numerator and apply the limit to the denominator. Okay, here I'm going to do it, let's choose a orange. So I can take the limit as x approaches 0 of this expression 1 plus log x plus 1. Okay, and these parts, then we can do work out these limits separately, because I can easily work out the limit of all these parts. So the limit of sine x as x goes to 0, that's going to be equal to 1. I'm just going to do it off to the side here. This is equal to, the sine part is equal to 1 to the power of n, okay, where n is unknown. I can multiply it with the limit of cos x as x goes to 0. So as x goes to 0, cosine of x is equal to 1. Okay, sorry, I made a mistake with the sign. The sign is actually going to 0, isn't it? Okay, sine x as x goes to 0 is equal to 0. Plus, okay, so we can take the limit of e to the x separately. As e to the x goes to 0, as x goes to 0, we get e to the 0, which is 1 in the numerator. And then we can work out the denominator. The limit as x goes to 0, this is going to be log of 1, which is 0, which ends up being 1 plus 0, or just 1. So this works out to be, well, that first part is equal to 0 plus 1, so the limit is equal to 1. And notice that we can do the limits of these these component parts individually and apply and combine them together afterwards. So, in a case like this, we can take the sine limit of the sine function independently of the cosine function. So limit as sine x goes to 0 and multiply that with the limit of cos x as x goes to 0. Okay, so that limit of sine x going to 0, that's going to be equal to 0 times cos of 0 is 1. So we have 1 times 0, so that's equal to 0. So there's our limit. Now we could also do some algebraic manipulation here because there's an identity involved here. So alternatively, I'll call this 2. Alternatively, we could apply the limit to the identity. This is 2 sine x cos x is sine 2x. And I can say this is 1/2 sine 2x. As x goes to 0, the 1/2 can be applied afterwards. If I let sine 2x go to 0, it ends up being sine of 0, which is 0. 0 times 1/2 gives us the same result of 0. Okay, so these results actually confirm each other. And for one, I just did the limits individually. The other one, I used the identity and applied the limit. So we could do the same thing here. We could use an identity, or we can, again, apply the limits independently of each other. Okay, so limit of as x goes to pi over 4 of sine x. Okay, this is going to be equal to 1 over root 2. The limit as sine x goes to, limit as x goes to 0 of cos x, not 0, but limit as x goes to pi over 4 of cosine of x. Okay, that's going to end up being equal to, 1 over root 2 as well. So when we multiply those together, okay, we end up with the limit equaling 1/2. And again, if we applied the limit to this form, we would get the sine of pi over 2, which is 1 times 1/2. Again, we would get the same limit. You doing it algebraically or doing it independently using some limit properties. So the same thing here, we could probably figure this out, using strong over weak arguments, but we can do this independently. So I take the limit as x goes to infinity of e to the negative x over limit as x goes to infinity of x. Here this is going to be equal to e to the negative infinity power, which is 0, divided by infinity. Well, that's going to be 0. Okay, and we can kind of see that e to the x would actually go in the denominator, so we have 1 divided by a very strong function. That's going to give us 0 as our limit. Okay, so those are applications of limit laws, and we can simplify our expressions using these limit laws. So here's another one where we can take the limit of 3x over 3, sine of 3x over 3x. We can do a little trick. So we know this fact. Okay, we know that this is an identity, sine x over x. The limit as x goes to 0. This is an established limit. Okay, we should really be using this as identity. So how can we use that fact to do this one? Well, what we can do is we can group that together like that. We can do a let statement. Let x 3x equal a. So in the end, we can just say, well, I can change this, and as 3x goes to 0, a is going to go to 0. So I can just let's say limit as a goes to 0 of sine a over a. Well, that's equal to 1. So this must also be equal to 1. Okay, and one way we can think of this is, if we think of the 3x as the length of that red curve, okay, so the length along the arc is the angle, or the x3x value, and this vertical line represents the sine value. Okay, if I want to know the vertical value of this compared to this arc length, well, as it goes to 0, we saw before that those lengths are essentially the same. As we go to 0, this arc straightens out, it looks more straight, and so we would then say it compares to that vertical line in a 1-to-1 ratio. Okay. Now we could also even further generalize this, and we can say this: sine of ax over x. Okay, so this is the limit as x goes to 0. Well, this really is this. So how does this arc length compare to, okay, and kind of imagine what this looks like. As we go close to 0, sine of ax, okay, is going to be this length here. We'll call that ax. And we want to compare that, and there's 3x here. Okay, so there's ax, and this length here would be 1/3 x, or just this length from here to here is equal to x. So how does this ratio compare? Well, this is going to be essentially ax to this vertical line. Okay, so maybe I'll try to be a little bit more clear about this. This purple line compared to the vertical line here is essentially going to be a 1-to-1 ratio as we get closer to 0. And if this is a 1-to-1 ratio, this shorter piece, which is the x in the denominator, should be a 1-to-3 ratio. Okay, so if a was equal to 3, we can just say this is 3 to, this would be 3, the sine x, so sine 3x would be 3 to a length of 1 along the x, or 3. And we could generalize this to a and say that this is going to be then equal to a, okay, because this will just be ax, and this is going to be 1 over a ratio to that. So this is going to be 3 times longer. So this, or sorry, a times longer than this length. So we end up with this ratio of just a. We can actually generalize this as well, and this we can use this as an identity too, if we want. Okay. Now we can justify this later with some other ways, but this is good to know as an identity, as this one is too. This is just an extension. This one is just an extension of our original identity here. Okay. So doing these next ones, how can we apply this? Well, we can use some limit laws to help us out here. Sine x over x squared. What we can do is this. We can say that this is a limit as x goes to 0 of sine x over x. Well, we know that's equal to 1. And we can say that, combine that with the limit as x goes to 0 of 1 over x. And this would be applying a limit law. We can just split off that denominator in this way. And we can get this. 1 times, well, 1 divided by x, going 1 divided by 0, from the positive side is going to be positive infinity. Okay, so we're going to end up with positive infinity. And if we actually look at this graph looks like this. It's just going to be kind of go in and then like this, and then it's going to shoot off like that. Okay, and then from this side it's going to do the same, and then it's going to shoot off going down like this. Okay, from the negative side it's going to go down. From the positive side, essentially, it's going to be behaving like 1 over x near 0. Okay, in both cases, whether you're going from the negative side or positive side, it's going to be behaving like 1 over x. What about this one here? Well, how can we deal with this one? Now we're squaring it. So this one we can use this limit law. So if I do this, I can take the limit as x goes to 0. It says for a positive side, but in fact this one doesn't really matter. And I'm going to do this. I'm going to take sine x over x. And I'm going to take that limit and square it. And that's the same as squaring the numerator and squaring the denominator and finding the limit of that. So this now becomes much easier because I know the limit of sine x over x as x approaches 0. That's going to be equal to 1. That becomes 1 squared. So we end up with a limit of 1. And if we were to graph this again, we can see that that is truly the case. So this one here, as x goes to 0 from the positive side, well, I know that I can do this. The limit of, as x goes to 0 from the positive side, of log of x plus 1, and then I can apply the limit as x goes to 0 from the positive side of cos x. Okay, so I can split off that limit in this way. I can apply the limit of the base and limit of the exponent. And limit laws allow me to do this. So as x goes to 0, the base becomes log 1, which is 0. The limit as x goes to 0 of cos is going to be equal to 1. We end up with 0 to the power 1, which is 0. And we could do the same thing.